It's more like work in pre-progress. So let me go ahead and give you some references for the stuff that I'm going to talk about, which is the theory of SOGATs, second-order generalized algebraic theories. So kind of the original reference on this is Taichi Uemura in I think 21 and 23, and so I think he introduced the term second-order generalized algebraic theory. There's a recent paper by Capozzi, and Suzumi Z, which is, I don't think that's published anywhere. I think it's just on Amber's website. So yeah, read that preprint. That kind of goes into a lot more detail. There's a paper by Altenkirk, Shamoon, hope I'm pronouncing that right, Capozzi, and Schulman. That was also 2024. And so this applies the stuff I'm going to talk about towards the theory of internal parametricity. And then there's also a nice, Raphael has a nice presentation in the paper on external univalence. I think that was 2022. And so yeah, part of my presentation is kind of based on that. And then I have my preprint this year, which also goes into some detail on this. And so as you can see from these year numbers, this is a very fresh innovation in the semantics of type theory, and it's a very active area of research. And there's still some pretty big open questions that we don't know about SOGATs that, and that's kind of what I want to be talking about here. Where did I put my chalk? Let's change colors. Can we see red? That looks good. Okay, so I'm going to write down a SOGAT. And so this is going to be a SOGAT for just basic type theory. And so type theory, we have types. And so you can think of this U as just kind of like sorts, or and so we have a sort of types. And then for every type, we have a sort of terms of that type. And I'll explain U star in a moment. And then this is just kind of boring type theory. We don't really have anything here, so let's also throw in pi types. And so pi types are, well, if I have a type A, and if I have a thing that turns terms of A into types, then I have a new type pi of those things. And that's subject to, I want to have a lambda rule that says that if I have some way of turning terms of A into terms of B of A, then that is a term of pi AB. And so this is a really nice way to represent type theory, because we don't have to mess around with a bunch of context and substitutions and context extension and state a bunch of laws. We can just write out like type theory as it's meant to be. And this is much closer to how like we intuitively think of a pi type. When I think of like how to form a pi type, I don't have context extension in my head, or maybe I do because I'm kind of a logician. But when we use pi types, we think of them as, oh yeah, if you have some type, then in order to form a pi over that type, then you need some kind of types indexed over terms of that type. That's more intuitively how, and in order to write a lambda abstraction, then you need to say for each term of the base type of type A, you need to give a term of type B of A. So this is so much closer to how we actually think and work with type theory, and it's devoid of a lot of the annoying details that don't actually matter. And moreover, this is or kind of a more technical way to say some of that is that this is a higher order abstract syntax. In that we've heard a lot today about variable binding and substitution. I'm doing variable binding here using these kind of a meta-theoretic function. I think I probably want a parenthesis here, I think, by the way, but I'm using a meta-theoretic function. So the variable binding that's happening here is a function. The variable binding that's happening here is a function. I don't have to worry about context and indices and all this stuff. But the kind of downside of SOGATs is that they don't have really nice model theory of their own. If I want to talk about syntax or as like the initial model, then what I ultimately want to do is I want to translate this nice SOGAT representation into a more familiar form, namely a GAT representation. So let me try to use blue for that. So we want to have a generalized algebraic theory, i.e., in this case, it'd be a CWF with pi types that represents the same thing as this SOGAT. And so it turns out we can do this. That we have this process of de-SOGATification, that we can turn a SOGAT into a corresponding GAT. And so this uses the pre-sheaf model. So I'm just going to keep getting out more and more chalk. So the idea of representing higher order abstract syntax in pre-sheaf models is largely due to a paper by Hoffman, which I think was 99. So that's the old paper on this list. Although many of these ideas have traces like much further back. And so the idea is we're going to use a pre-sheaf model, and what we're going to do is we're going to translate this SOGAT representation as living inside the pre-sheaf model, and then we're going to a pre-sheaf model on some unspecified category, and then we're going to use this as specification to get the structure that we need in our GAT, like structure on top of the category in our GAT. So we're going to have some category C, which is all right, GAT. And then we're going to look at the pre-sheaf model. So I'm not going to spell out all the details, but I'm sure many of you are well familiar with how pre-sheaf models work. And so it's the pre-sheaf model over this unspecified category C. And so my contexts are going to be pre-sheaves, so C up to set. And if I want to be really technical, there's a few size issues here that I have to be careful about, but I don't care about those, so I'm gonna kind of ignore them and trust me that it all works out fine. And then the only other thing, so I'm gonna decorate the components of this with little hats because otherwise we're gonna go insane in just a minute. So in the pre-sheaf model, a type in a context gamma, and gamma is a pre-sheaf, is also a pre-sheaf on the category of elements of gamma. So I'll use that fact in a minute. And then we could spell out more. We could say, we can define what term hat is and what, we have the empty context, which is just which is the terminal object of this category. And then we also have a universe. Am I writing too low here for the people in the back? No? Okay. We also have a universe, which is a tie. It's actually a large type, but I'm going to write large very small because it doesn't matter, which is a large closed type. And the property that it has, so one of the key properties I'm going to use here, is that a term in any context gamma of this universe U, if I weaken it to live in gamma, that's what I want is that this universe classifies types. And so this is going to be in bijection with tie of not one, but of gamma. So for any context gamma. And you can figure out what the definition of U has to be just by a really nice Yoneda argument that I would love to include, but I'm going to skip it because limited time. Okay, so then I think that's all the ingredients I need. And so then what we can do is, so one more color. What we can do is we can translate this into, this is in pre-sheaf semantics. And so if I say tie colon u, if I'm interpreting that in the pre-sheaf model, what that means is that tie is a Tim hat in the empty context of u. So this is why I wanted hats on these, is, so I didn't get confused. And then we can do some calculations. So maybe, I think I won't need this for a minute, so let's send that up. Ooh, sorry. Okay. Okay, that's all we need. All right, so we can calculate that Tim hat of 1u, well, by our classification by the fact that u classifies types, we have that this is the same thing, or this is in bijection with tie hat of the empty context. And so this is, by definition of what we just said, this is the category of elements of the terminal context pre-sheaves on that. And the category of elements of the terminal pre-sheaf is isomorphic to just the category itself. And so we get here COP to set. And so this tells us what we probably already knew, is that we have a pre-sheaf tie of the form COP to set. And so that's just the first step, but we can go through each line of this SOGAT representation, interpret it in the pre-sheaf semantics, and then do some calculations and find out what it ends up being. So if I follow through Tim over here, then it'll wind up being what you might expect, is that Tim is a pre-sheaf on the category of elements of time. And I haven't mentioned this little u star here in a minute, but the reason this is u star, so in the SOGAT representation, notice that the only things that are appearing negatively are these terms. So Tim A is allowed to appear negatively. And that's because it's u star. So u star are the things, u star are the things that are allowed to appear negatively in an argument like this. That's why it's a SOGAT, is that it's a second order. I'm allowed to do these kinds of second order terms like this. And so how that's like cashed out in the pre-sheaf semantics is that u star is the universe of locally representable pre-sheaves. And so I don't think I have time to get into like the technical definition of what locally representable is, but you can define u star as similarly to how you can define u and do the calculations. And what it ends up being here tells you that Tim here is locally representable with respect to tie. And what that means is that we get a extension operator which takes any I in C and any and any tie in I, and gives me back another context. And subject to the isomorphism that if I have morphisms from say J into I extended by A, those are in bijection with run a little low on room here, a morphism I from C Ji and Tim of J of A substituted by I. So again, in the preprint and in several of these works, the technical details of what local representability means and why it gives us this kind of an operator is spelled out in more detail. But you can kind of see this as I mean, it's a version of representability in that this I extended by A is serving as a kind of representing object for Tim over Ty. But it's a kind of a relative representability, not kind of an absolute representability. All right, so this is the kind of basic setup. And this is what's really nice about SOGATs, is that we can use these as specifications, we can use these as specification language for writing down our type theory without having to worry about all these substitutions and context extensions and stability under substitution and all that jazz. But if we need to deal with that kind of stuff, then we can automatically generate it by this kind of a process. We can translate our SOGAT into a GAT, like I said, where it's more convenient to talk about syntax and initial models and various things like that. All right, so the question I have is what, so this paper by these two authors spells out that for basically any structural type theory like this one, you can perform this kind of translation. They do it more exactly using some kind of signature languages for SOGATs and GATs, but yeah, for any structural type theory, you can perform this as kind of a translation. But what's kind of left open is what you can do for substructural theories or modal type theories. And so that's the kind of open question: is can we do like a modal? Can we have like modal SOGATs? Can we do a SOGAT representation of modal type theory? And to kind of explain why that's difficult, let me pull on those of you who were at my talk yesterday. You'll remember that I had, so these are kind of a simpler kind of modality than what we had in the last talk. Ultimately, what I'd like to move towards is a SOGAT representation of multimode type theory as we just saw. But in the category model that I was talking about yesterday, what we had was operators like this. We had a minus operation, which in this category was an endofunctor on our category of contexts, and then we also had a negative context extension operator, which took a context I and a type in I minus and gave us back a new context. So it was a negative extension. And then we also had an operation on types, so tie I to tie I, which, I'll write the law, was subject to the law that if you did A substituted by I and then minus that, that's the same thing as A minus substituted by I. And so that's the question: can we do a SOGAT representation of this? And that's difficult because notice the whole point of SOGATs was to abstract away from talking about context, to abstract away from talking about substitutions. But then here we have, so then how do we talk about an operation on contexts when there are no contexts? So So this type operator we can do. We can say that we have a minus operation from tie to tie. And so if you spell that out via the presheaf semantics, then that's going to give you a natural transformation from the tie presheaf to itself, which is great because that's exactly what this kind of thing is that for every I it goes tie I to tie I, and then this is naturality right here. But the context and context extension is a little bit more tricky. And to see, so to see what the kind of how to do that was to note what the corresponding law was for the negative context extension. So the rule there was that if I negatively extend A, if I have morphisms into I negatively extended by A, then that's in bijection with term in J minus, A minus, and minus here. So I throw on a bunch of minuses. And so if you squint at this for long enough, you'll realize that this is also a kind of local representability here. Namely that if we, namely that if, sorry, I'm going to kind of violate my space thing and move over here now. Namely that if we have, if we define tie minus to be tie after the minus operation, then what this law is saying is that Tim, and then we can define Tim minus of J of IA to be Tim of I minus A minus, which if you kind of go through the algebra and remember that minus composed with itself is the identity, then you'll see that makes sense. So what this law is saying is that Tim minus is locally representable with respect to time minus. And so what we can do is we can have two ties and two Tims. So I'll write S here to mean either either plus or minus. So yeah, S equals plus or minus. And so and then we can fix our pi types so that this is tie minus and Tim minus, but then it still goes to tie, and same here. And then if we do the SOGAT translation, we almost get this endofunctor. So there's a little bit of a mismatch, and it's not quite clear how to solve that. So I kind of discussed that issue a little bit more at length, and have kind of two different notions of what the GAT of this kind of polarized type theory is, as I call it. But there's clearly some work that needs to be done there. And more generally, if we want to represent these kinds of these kind of like substructural theories or these kind of modalities, if we want to elevate them from GATs to SOGATs, then we need some kind of expansion of the notion of SOGAT. We need to kind of extend or strengthen the theory of SOGATs to be able to encode these kinds of theories. And so that's really what I am planning on studying in the coming months and such. And so I'm happy to say that my this cost action is funding my research visit to Budapest this summer to talk with Ambrish Kaposi and friends about how to do these SOGAT kind of representations for directed type theory, for modal type theory, for multimodal type theory, for linear type theories, and various other kinds of things that aren't currently covered under the paradigm. So that's all I'm going to say for now. So yeah, thank you for listening.
Okay. We also have time for short question. Make me run.
Yeah. So now, I mean, you consider a very concrete example, and so you go from this SOGAT to GAT, and then this connection with this pre-sheaf semantics. But is this something more general, or is it just something that works for this specific signature?
Do you mean like this specific SOGAT, or?
Yes.
No. So yeah, I should have emphasized this more. So this is an extremely broad, I mean, as broad as, there's so many different things you can represent with GATs, and there's so many different things you can represent with SOGATs. So this is just a basic type theory. I could go on to, add sigma types or, whatever kind of flavor of. So I said, yeah, they've kind of covered basically any structural type theory you can represent as a SOGAT, and you can still perform this kind of kind of translation, provided you obey things like the rule, the kind of syntactic rule I said that only things in U star can appear negatively. But yeah, other than that, yeah, this is a very broad, and so some other examples that. So I think this paper has. Does it for, they included an example like System F type theory. You can do this for first order logic. Like I said, this paper has some, does this for internal parametricity. So yeah, it's a very, very broad framework for reasoning about type theories.
Yeah, but so it's, I mean, as you say, these are all example, but is there like a formal connection between, let's say, arbitrary SOGATs and GATs? So I don't know, something like, I don't know, an adjunction or even an equivalence or something.
Yeah, I mean, yeah. So I'd probably look in this paper for a better answer to that, because they developed, like I said, a kind of a theory of signatures for SOGATs and GATs, and spell this out as an explicit translation on the level of the signature languages. Whether that's like constitutes an equivalence or an adjunction, I'm not sure off the top of my head.
Okay, thanks.
Yeah. Right.
Okay.
Okay.
Okay. Well, I think now we can go happily for dinner. So thank you very much.
Thank you.